parabolic reflector here. Okay, this is kind of another antenna here. Okay, so what exactly the figure consists of here? The figure consists of this, particularly this is f here. What is f here? F is nothing but here focus here, capital F. This is nothing but here focal focus here, and the O is nothing but your vertex here. You can see in this particular figure, O is nothing but your vertex here, and F is nothing but your focus here. So F is nothing but your focal length F here. Okay, so O dash is nothing but your O dash is written. No, this is nothing but your axis of the parabola here. Okay, now how exactly the parabola is defined here? Now a parabola can be defined as, like as per the statement which we have written here. So it is defined as a locus of a point here, which moves, okay, which moves in such a way that its distance from the fixed point plus its distance from the straight line called director is constant here. Okay, so now see here what is the definition states here. So whatever our parabola will be defined as locus of a point which is going to lie on this particular half curved surface here. Remember, this is going to lie in this particular half curved here. Okay, the point. So the locus of a point which moves in such a way that its distance from the fixed one. This is the fixed point here. Remember, this is the fixed point called as focus here. Okay, okay. Plus its distance from the straight line. This distance from the straight line, okay, called the dielectrics, is constant here. Now, this particular thing is a two-dimensional plane curve here. This could be represented by this equation here. Remember, fp1 plus p1 dash. Okay, see here, fp1. This is f here. This is p1 here. Okay, p1 dash here. Okay, this is what is the focus here. Its distance from the fixed point. This is nothing but a fp1. Okay, plus its distance from the straight line. That is nothing but pp dash here. Okay, this is what we have written here. fp1 plus p1 p dash is equal to fp2 plus p2 dash here equal to fp3 plus p3 dash here is equal to constant here. Okay, that is fp1 plus p1 dash is equal to fp2 plus p2 dash here. Okay, that is what is written definition according to the definition here. Okay, now how exactly the equation of the parabola curve could be written in terms of its coordinates here. Okay, in terms of coordinate here, y square is equal to 4fx here. Okay, so the open mouth is nothing but here. This is the capital D represented by the capital T here. Okay, now, okay, after the parabola is known as the aperture here. Remember, this is what is known as aperture, and we wanted to find the ratio of this capital D here. This is capital D, ratio of the capital D, or you can say a ratio that is whatever the focal length is there, small f, which we have represented here, small f, focal length, f divided by capital D is known as the f over D ratio here. Okay, remember here, whatever this f over D ratio is, that is going to vary between 0.25 to 0.50 here. Okay, now let us consider now the description here regarding or you can say the operation here. Let us consider a source here. Let us consider a source here of radiations here that is going to be there at the focus here. Let us consider this is the point here where exactly we are going to have the source of radiation here, right? Okay, so let the ray start generating here, or let the ray start moving here. So at an angle here, at an angle theta with respect to the parabolic axis O dash here. This is the parabolic axis here, and there is a source here which is going to generate certain radiations. See, there are four waves are generating: one, P1, P2, P3, and here and you can say where the label has been not given here. Till then, you can consider the P4 here. Okay. So now what is going to happen here? This particular wave which is going to be generated, or a ray that is going to be generated by this particular source at the focal point or focus point here, which is going to strike to this particular curved surface here. Okay, just remember here, curved surface where it is a point striking here at the point P1 it is striking, P2 it is striking, P3 it is striking, and it is also striking at a P4. Let us name it as a P4 here. Okay, now according to the law of reflection here, what is going to happen here? The angle of incidence is equal to the angle of reflection here, right? Reflection, sorry. Okay, so will be equal here. So thus what is going to happen here, if at all that is the case here, angle of incidence is equal to the angle of reflection. What is going to happen here, whatever the reflected waves are there here, those are all parallel to what here, axis here, parabolic axis. Remember here, all this uh, which has been reflected here, no, that has been all parallel to the what here, parabolic axis here. All the waves, okay, which are originating from this particular point called as the focus here, will be reflected here. All the rays, and they are parallel to what here? Parabolic axis here. Okay, reaching the aperture. This aperture is nothing but this is the aperture. Capital D is nothing but here aperture here. That is mouth of the whatever the parabolic reflector is there. Reaching the aperture, okay, reaching the aperture at a, which at a plane here, which are always in phase. Remember here. Since all the waves are in phase here, what is going to happen here? A very strong and concentrated beam radiation is along the parabolic axis here. Okay? If at all the waves which have been reflected from this particular curve surface here, okay, are in phase here, then you will be having the concentrated radiation here, okay, which is along the parabolic axis here. Okay, this much you remember here. Now, if at all we consider that if the beam of parallel rays is incident on the parabolic surface here, okay, if at all in this particular figure, if at all this is this figure, you can, if at all we have a beam of a parallel ray, this is the beam of a parallel, how many rays we are having, 5 rays we are having here, right? If this particular beam of rays here which are parallel to each other are very incident here on this parabolic surface here, what is going to happen here? Okay, so if at all it is been incident on this parabolic reflector here, those all rays will be focused at one point, that is called as a f here. Okay, if this parabolic reflector is the three-dimensional curve here, remember. Okay, so if the third Cartesian coordinate z has its axis here, okay, if at all we have another axis here, okay, that is nothing but here another than the x and y axis here, we are having z axis here, then if that will be perpendicular to the x axis and the y axis here, the equation of the parabola can be written as y square plus z square is equal to 4fx here. Okay, okay. Now if at all the radiation pattern of an antenna employing the parabolic reflector has a very sharp major lobe here, if at all whatever the rays that have been there here, okay, which are incident on this parabolic reflector, that two parallel to each other, and if they have a very sharp major lobe and number of minor lobes which are smaller in size, okay, then whatever the narrow major beam is there is in the direction of the paraboloid axis here. Whatever the beam will be there, it will be in this directions here. Okay, the narrow major beam will be in this direction of the parabolic axis here. Okay, now paraboloid will produce a beam of radiations here. If at all whatever the aperture is there which we considered, okay, it is a circular aperture and it is very large here, the beam width within first null can be represented as 140 into lambda divided by d here. Lambda is nothing but a free space wavelength here, and d is nothing but a diameter of the aperture here. Again, if at all we wanted to find the half power beam width here of this particular larger circular aperture, then it is nothing but a 58, okay, into lambda divided by d here. Now, how exactly we find the directivity here? Directivity is nothing but here. Again, you can take this standard equation here, that is 4 pi a divided by lambda square here, which we have derived in the previous classes here in the third model here. That could be taken. If at all we have a circular aperture here, then a is equal to pi d square divided by 4. You can substitute it instead of this particular a here. This is nothing but here area of the circular loop here. Okay, then so if at all we substitute here, we will be having a d is equal to 9.87 capital D divided by lambda whole square here. Okay, now if at all we wanted to whatever the feed antenna is there here, feed antenna is nothing but here you can primary antenna, or you can say where exactly you're giving the source here. If the antenna is not isotropic here, not isotropic means what here? It is not going to generate the radiation in all the direction here. Okay, thus does not radiate uniformly. Okay, if there is radiations which are not uniform in nature, means what is going to happen here is there is an introduction of the what you can say certain distortion here. Okay, the surface is paraboloid here and it is not uniformly illuminated here. If the surface is paraboloid and it is not uniformly illuminated, means as there is the gradual tapering towards edge here. This results in less capture area, which is smaller than the actual area here. Okay, always remember here, if this particular surface here, whatever the surface we are going to consider as a paraboloid here, if this particular surface is not uniformly illuminated here, what is going to happen here is that the actual the capture area will be less compared to the actual area here. That is what it is a meaning statement meaning here. A naught is nothing but here your what is that capture area here. A is nothing but here your actual area here. Okay. Now the power gain here. Power gain of the circular aperture of the paraboloid with respect to half wave dipole here. Directly it is being taken here. Okay, is given by, if at all we need to consider here the a capture area here. Okay, so if at all we wanted to find out the power gain of the particular helical antenna here, sorry, parabolic reflector here. So 4 pi a naught is there. A naught is nothing but a into a here. What is a here? Pi t squared divided by 4 here, right? So you can substitute the value and get the answer here, that is 6.389 divided by lambda whole square here, right? This is how we can get the information, or you can say the equations relating to the parabolic reflector here. Remember here, this is the figure here. Figure description has been given here. This equation is very important, concerned with the definition will be written here. Then the parameters are there here. If at all we consider a source at the focal point, how exactly the rays will be reflected here, and if at all the angle of the reflection is equal to the angle of incidence, then what is going to happen, resulting into the reflected ray which are parallel to the parabolic axis here. Okay, right. And if they are all in phase here, a strong radiation will be generated here. If the parallel rays are been incident on the parabolic surface here, we are going to have, okay, we are going to have a major lobe here along the parabolic axis here. Okay, and then we find out the beam width first null and half wave beam width, directivity, and the gain here. Now what are the advantages here? Advantage is high gain. Parabolic reflector antennas are able to provide very high gain here. Okay, the larger the dish in terms of wavelength, the higher the gain here. I think you know the direct yesterday I have told you regarding the dish antennas here. Larger the surface area will be having, the higher the gain here. Directivity will be high here. Okay, disadvantage is nothing but here, it requires a reflector here and the driver element. Okay, the parabolic reflector itself is only a part of the antenna here. It requires a feed system to be placed at the focus of the parabolic reflector. Yes, cost is also increasing here. I think as you require more elements here, the cost also going to be increasing here. It's just not a just a parabolic surface is sufficient here. We need to have the reflector and the driver element here, and size is not small as compared to other types of antennas here. Okay, what are the applications are there? I think you know direct broadcast television here, DTH we can say, no, satellite television has become a major form of distribution for television materials here. Microwave links you can consider here. Okay, and radio astronomy, where high levels of gain and directivity are required, satellite communication here. These are the four areas here where our parabolic reflector it has been utilized here. Okay, this is the end of what you can say that parabolic reflector here. If at all you have any questions relating to the parabolic reflector and helical antenna, please